Welcome to qnawire.
So let's draw the picture first and then we can see how to solve the problem. So we have a bar over here and this bar is resting on the axle. So let's call this axle. Then we have two separate masses that's attached to the bar, and each of the masses weigh 2.5 kg. So what happens is one of the balls gets detached. So let's say this one gets detached. So then what happens is we have the weight, we have a disbalance of weight. So that's why this ball will try to come back to here, and because of that there will be a rotational motion. So we need to figure out the acceleration or the angular acceleration because due to this scenario. So to do so, we can solve the angular acceleration using the torque equation, where torque is equal to the moment of inertia times the angular acceleration. Now, if we want to figure out the moment of inertia, we know that we have two separate things. One is the bar and one is the object that is, or one is the ball that is attached to the end of the bar. So this moment of inertia will be an addition of the moment of inertia of the ball plus the moment of inertia of the bar. So now since the bar is rotating uh, at the axle, so we'll have 1 over 12 m bar L squared, where L is the length of the bar, and then for the ball it's just m ball times L over 2 squared. And the reason it's L over 2 is because the bar is rotating along this, and the distance from here to the axle is L over 2. So so what happens is we have another way of defining torque here, and that's the following. So since the bar is rotating, so there will be a force that's acting downwards. So let's call it m ball g, and that is acting tangentially at this position. So we'll have the force times r, which is in our case L by 2, to get the torque, and that's what we got here. So this is one way of getting the torque. So we can equate this torque with our standard definition, which is moment of inertia times alpha z. So alpha z is the angular acceleration, and as we mentioned, this is our total moment of inertia. So if we combine these two and solve for alpha z, we get this following expression. So our given values for m ball is 2.5 kg, m bar is 3.8 kg, and L is zero point 0.8 meters. So we can plug those numbers over here and see that alpha becomes 16.3 radians per second squared. In part B, as the bar is rotating, the moment of the weight of the ball decreases. Uh, Sorry, there should be a space here. Yeah, as the bar rotates, the moment for the weight of the ball decreases because the ball is no longer attached to the bar. So that's why the angular acceleration of the bar will decrease as well. And for part C, if we go back to the picture one more time, we'll see that at the vertical position, we'll have something like this, where the distance from here to here will be L by 2. Now, if we consider this as our origin, so here y is 0, and so that means let's call this point number 1, and let's call this point let me draw the ball here, right? Let's call this point number 2. So we see that at point, if we consider this as our origin, so that means y1 will be 0 here, but y2 will be negative L by 2. And the reason for the negative sign is we consider this as our origin, and we're considering upward direction as our positive y direction. So we can use the energy conservation here. So we'll apply energy conservation at this point when the system is kind of stable. It hasn't started rotating, and then at this point when this bar is kind of swinging, so it's trying to go this way. So that means this is our conservation of energy equation. But at this point, when the bar is horizontal, we don't have any kinetic or potential energy since it's at rest. So that's why we set that to 0. So these two terms are 0. But there will be some, and at the second point, when the bar is around here, we'll have both kinetic energy and potential energy. And the potential energy will be due to the gravitational potential energy, but the kinetic energy will be due to the rotational motion. So in terms of rotational motion, the kinetic energy is half of I omega squared, and that's what we used here. And we know that I is the addition of I ball plus I bar. So we wrote that. Then there's a negative sign over here, and the reason for that is we took K2, we kept K2 here, and we took U2 on the left, and that's why we got a negative sign. Also, we have a negative sign over here as well, and the reason for that is mentioned here when we say that this is our origin, so y2 is negative. So this is the equation that we get, and we can solve for omega from there. So if we solve this equation in terms of omega, we get this following expression, and we simplify that then we already know these terms, and we can see here as well. These are the values that we'll be using. So if we plug those numbers over here, we see that omega is 5.7 radians per second. Thank you.